Good day, everyone. My name is Tieu Siu Hui, and I will be presenting the introduction for our project, the semiconductor-based smartphone cooling system. As we know, the modern smartphone utilizes the high-performance processors and fast charging to enhance our experience in game and multitasking. However, the high power consumption lead to excessive the heat generation. So this result in two major issues. The first one is the thermal throttling, which causes the reduced speed and lagging. The second is the hardware risk, such as the battery degradation and internal component damage. So to solve this, we developed an external semiconductor-based cooling device using the thermoelectric technology. The key technology is the pillar effect, which allows for active and rapid the heat dissipation direct from the phone surface. So by using the method, we can maintain the peak smartphone performance and significantly the prolong if over a hardware lifespan.
And greeting to everyone. My name is Sridharan, son of Saravanan, and today I am going to talk about the objective from this project. In this project, our research focuses on developing on effective cooling solution for smartphone, especially during high performance usage. The first objective of this research is to design and fabricate a semiconductor-based smartphone cooling system using a thermoelectric cooler, also known as a TEC. This system aims to all actively control and reduce heat generated by the smartphone. The second objective is to reduce the surface of temperature of smartphone during intensive activities such as gaming and video streaming, which often cause overheating and performance throttling. Next, the project aims to develop a portable and easy to use cooling device that's suitable for daily smartphone users without affecting comfort or mobility. Another important objective is to analyze the cooling performance and operational stability of the system to ensure it works effectively, which is reliably over time. Finally, this research also focus on ensuring that the device operates safely while minimizing its environmental impact. In conclusion, these objectives guide the development of the practical, efficient, and user-friendly smartphone cooling system.
Hello, my name is Sheikh Imran Bashir Akbar and my matric number is B1325-10825. So this is our product design. From the front view, you can see the compact box structure that houses the cooling system. The smartphone is placed directly on top of the cooling surface to ensure the maximum heat transfer from the phone to Peltier module. So the simple rectangular design have maintain stability and ease of use. From the top view shows a flat contact surface where the smartphone is positioned. A digital temperature display is included to monitor the temperature in real time, allowing users to observe the cooling performance clearly. So these features help demonstrate the effectiveness of the cooling system during operation. So the last one is inside the box. Inside the box is have the main component include a Peltier module for heat transfer, a heat sink and cooling fan to dissipate heat from the hot side. So proper wiring and power connection to ensure safe operation. The Peltier module absorbs heat from the smartphone and transfer it to the heat sink, where the fan helps remove the heat efficiently. This prevents overheating and improves smartphone performance.
Now we're moving on the requirement total cost. So to build this functional prototype, we utilize the following part. The first one is the copper plate for If I say heat absorption, the costing is 29 ringgit 66 cent. Item 2 is PVC strip for the trussing. The cost is 8 ringgit 69. And item 3 is the pitted module with a cooling fan and heat sink. The costing is 41 ringgit 20 cent. And a temperature sensor of monitor the cooling performance. Costing is 6 ringgit 50 cent. And a power adapter to provide the stable energy costing is a 20
Okay,
ringgit.
now I will explain the video operation. Basically, our product is so simple to demonstrate. We just have to on the switch, and as you can see, before I switch the switch, the room temperature is 27.6 degree, which is a room temperature, but this is a late night, so it's a bit cold. So we on, then we will wait a few minutes so the project and the system will run, and we have to wait like a 5 minutes to have a copper plate to be cool, and we just have to put a phone that overheating to this project right here, and the phone will be cooling down. So as you can see, the average temperature which is we can do is 26 degree, and the temperature we put the thermocouple in the back of the copper plate. Hi, my name is Muhammad Sazwa Arif, and I will present about a video operation and working principle. As you can see at the previous video, I have demonstrated how to operate our project, and I will explain about the working principle at our project, the heat transfer process for the working principle. First, we have the heat absorption, the source, which is the smartphone surface. Smartphone surface is high performance touch generate heat, and the copper plate. The copper plate is high thermal conductivity, rapidly pulls heat from the phone into the cooling system. So basically, like our phone that have a heat, and we can put it here, so the heat from the phone go into the plate. The second, the thermoelectric transfer. Thermoelectric transfer have a Peltier module, which is a DC power trigger the Peltier effect, creating a temperature differential. The cold side become the heat sink for the copper plate, and the hot sides pump all absorbed heat toward the back of the device. So basically, we use a Peltier to transfer heat to cold. So which is, even we use DC like this. I have a wire from the DC, but usually at the home we use a AC, which is alternative current. So we transfer it to AC. So we use this cable to DC to convert it to AC. So the third, the heat dissipation. The exhaust, the aluminium heat sink distributes the hot side energy across a large surface area and have cooling fan force airflow through the fins to expel heat into the surrounding area. Like our project have a cooling fan at the back, so if the peltier at the back got pump all the heats, so our cooling fan is to blow the heat at the back, so this project will not overheat because have a cooling fan to do the airflow at the back. The third is monitoring and protection, the brain. The temperature sensor feedback loops monitor real-time heat levels. PVC body is provide a safe isolate grip for the user while preventing condensation or electric leaks. So basically, this is our temperature sensor. So as you can see, at the room temperature right now is very hot, like 34 degree. So the temperature, we used to check the temperature at the copper plate. We put the thermocouple in the PVC body in this body, so that the thermocouple can detect temperature at the back of this copper plate. So the PVC body is this body. For the whole body, we used to provide a safe for safety for the electric leaks or to prevent condensation for this project.
Performance results. This slide shows the performance of the smartphone cooling system. Test environment. The test was conducted indoors in Malaysia with an ambient temperature of 30 degrees Celsius. Without cooling, during continuous high load usage, the smartphone temperature increased to 42 degrees Celsius, which may affect performance and user comfort. With cooling activate, after turning on the peltier cooling system, the temperature dropped quickly and stabilized within 5 minutes. So the final result is the smartphone temperature was successfully reduced to 26 degrees Celsius. So the key outcome, our system achieved sub-ambient cooling, which is 4 degrees Celsius, lower than room temperature, with a total temperature reduction of 16 degrees Celsius.
Let's move on to the ideas to improve smartphone cooling system. This section presents several proposed improvements to enhance the performance, safety, and the reliability of the smartphone cooling system. First, thermal efficiency and heat management. One major improvement focuses on thermal efficiency on the hot side of the system. A larger heat sink combined with a high RPM fan, it is proposed to improve heat dissipation and prevent heat saturation from the thermoelectric cooler. At the interface level, high-grade thermal paste will be applied to eliminate air gap between surfaces, thereby reducing thermal resistance and improving heat transfer. On the cold side, high conductivity thermal interface material or TIMs will be used to ensure maximum surface contact between the cooling plate and the smartphone, resulting in more effective cooling. Second, smart control and energy saving. To improve energy efficiency, pulse width modulation or PWM regulation will be implemented. This allows the power supply to the peltier module to be adjusted based on real-time temperature conditions. In addition, an automated cooling system with a feedback loop will be introduced. This system adjusts the cooling output automatically, preventing excessive power consumption and improving overall energy efficiency. Third, condensation and safety mitigation. Condensation is a critical safety concern. To address this, thermal insulation will be added around the cold plate and the minimum of operating temperature will be limited to remain above the dew point, preventing moisture formation. For electrical safety, all wiring and connection will be properly secured and insulated. The PVC enclosure will be also reinforced to improve structural durability and protect internal components. Finally, accuracy and longevity. To improve measurement accuracy, temperature sensor will be repositioned to ensure direct surface contact and recalibrated to provide precise temperature reading. In terms of durability, the system will be used to use more heat resistant and long lasting material to ensure stable operation over an extended period, so that these improvement ideas enhance thermal performance, reduce power consumption, improve safety, and increase system longevity. Overall, these enhancements contribute to a more efficient, reliable, and user-friendly smartphone cooling system. Thank you.
So, in the conclusion, design is successfully implemented a Peltier-based cooling system that outperforms conventional passive cooling method. Key achievement: speed address the limitation of slow cooling by achieving rapid temperature reduction within a short time frame. Optimized components such as a copper plate, plating module, and cooling fan. Copper plate is utilized high thermal conductivity for instant heat absorption. Plating module is to provide active, reliable heat transfer away from the device. Cooling fan for maximized heat dissipation for continuous operational stability. The system characteristic: the final prototype is simple, compact, and energy efficient, making it ideal for portable smartphone application. The technological potential is to demonstrate that thermoelectric technology is a viable and effective alternative to traditional bulky cooling system. For future roadmap, its performance can be further scaled through improved insulation, power optimization, and advanced heat dissipation techniques. Thank you so much. That's for our presentation.